So in this video, we're going to apply some of the rules we learned about current and potential difference in our previous videos to actually calculate things for given circuits. So let's say we've got a circuit set up here. What is the current and potential difference across two resistors in series for a given circuit EMF? Let's label some things on. So this is the setup we have. We have a cell with a potential difference of V, supplying an electromotive force of V to our circuit. We have a current, which we're going to give I, the symbol I. We've got resistors R1 and R2. We've seen previously that we use R to represent resistance in general. So when we've got multiple resistors, we simply put a 1 or a 2 by the side, depending on how many we've got. And then we've got a potential drop of V1 and V2 across these resistors. So what do we need to do? Well, the first thing we need to ask ourselves is, what do we actually know about this circuit? And the answer is, what we're saying is that we're given this V. We're told the power we're applying. For instance, you might have for a given battery, you'd be told the potential difference that would supply. So we know the potential difference our battery supplies, our cell, here, supplies to our circuit, and we know the resistance of our resistors. That's the other thing we know. We know that this has a resistor R1 and this has a resistance R2. Everything else we need to work out. So how do we start? Well, what can we say about V1 and V2 given that our potential difference supplied by our cell is V? And this is where we use that law we saw in our video on potential difference rules, where we remember that through the conservation of energy, we must have that the sum of our potential rises, which in this case is V, is just equal to the sum of our potential drops, which in this case is V1 plus V2. So let's write that down. So for conservation of energy, we must have that our potential rises, V, is equal to our potential drops, V1 plus V2. So that's told us the potential, that's given us a relation for the potential drops across these resistors. What's the next thing we know? Well, we know that our current through each of our resistors is the same, and I kind of implicitly said that when I just said we have current I for the circuit. That means the current through this resistor R1 is exactly the same as the current through the resistor R2. Note we have to specify V1 and V2 for the potential drops across these resistors. We don't need to do that for the current because the current's the same wherever you are in this circuit because we're in series. So the current through each component is the same. Remember, that's conservation of charge. What does that mean? Well, it means that we know that our law of, our definition, of resistance still applies. Remember, that's that R is V over I. So what can we do with that? Well, we realise that has to apply to each of our resistors separately. What that means is that R1 must be equal to the potential drop across R1, which remember is V1, divided by the current through it, which is I. And equally R2 must be equal to the potential drop across it, which is V2, divided by the current through it, which is I still. And we can actually rearrange that nicely.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.